Level 2 Wildland Fire, White Spar Road, and Copper Basin Road.
The dispatch comes in. There's a fire in the wildlands just outside a neighborhood in your response area. Normally, when we arrive at the scene, it's our job to size up the fire and devise a strategy that will contain it. But what do we do in those situations when our goal of containing the fire is no longer realistic? And it then becomes our job to defend the threatened neighborhood. A new strategy is needed for this scenario, and your success will depend on how well you understand fire behavior in the wildland-urban interface. Most firefighters are knowledgeable about operations and logistics for specific kinds of fires. If you're a structural firefighter, you know how to size up and extinguish fire in a building or home. Or if you're a wildland firefighter, you understand how to contain a blaze occurring in vegetation. Responding to fire in the wildland-urban interface, however, gets a little more complicated. Anticipating what fire will do in a community requires more than simply blending wildland and structural expertise. Now you're dealing with multiple ignitions, entire neighborhoods, and all kinds of natural and human-made fuels, all of which require a new understanding of fire behavior. So how do you anticipate where a fire will go and what it will ignite in a wildland-urban incident? To find out, let's take a look at one possible fire scenario. Let's say that your engine is responding to a fire that is rapidly approaching a neighborhood in your area. We'll call this community West Creek Village. For our purposes, West Creek is a fictional place, but it could also exist in your community with your terrain and fuels. Let's begin with some perspective. As you can see, West Creek is a low-density neighborhood of about 20 to 30 homes, nestled at the base of a small canyon. Some structures are even intermixed in the wildlands. Above West Creek, there is a rolling meadow where the fire appears to have started. The fire has subsequently descended into this forested area, near the community. It's our job to size up the fire and determine if it will threaten these homes, and if so, when. Once we answer these questions, we can then develop a strategy to protect the neighborhood. We'll assess three key factors: fuel, weather, and topography. Consider fuel and fuel loading. Looking at our landscape, we can assume that the fire moved very rapidly through this meadow. Why is that? As you can see, the meadow is composed of fine fuels such as dead grass and light shrubs. These fuel types ignited easily and burned quickly. As the fire reached the wooded area, the fine dead grass fuels ignited the undergrowth and dead wood, which, in turn, ignited the low-hanging tree branches. The thicker branches and shrubs took longer to combust, but now that they have, they will burn longer and more intensely than the grass, and they'll loft firebrands into the air. The second factor to consider, weather, has contributed to the fire situation. Temperature, humidity, and precipitation have a direct impact on fuel moisture and the ignitability of fuels. For example, recent low humidity in West Creek has dried out the dead pine needles, grass, and shrubs. And seasonal conditions have pushed temperatures near 90 degrees. The hot, dry conditions combined with below average rainfall have also dried the light vegetation. The slope aspect also plays a role in the fire's behavior. The side of the canyon that is burning is facing southwest. By the middle of the afternoon, the sun will be shining directly on the slope, further drying out any dead vegetation. And then there's the most unpredictable weather factor of all, the wind. In our scenario, the wind is gusting up to 30 miles per hour, down the canyon. The wind direction is driving the fire spread from the meadow into the trees, and is now moving it towards the community. Why does wind increase the spread rate of fire? One reason is that wind increases the supply of oxygen to the fire. But more importantly, wind increases the heating of fuel in front of the flames. The wind tilts the flame closer to the fuel and ignites it faster, thus increasing the fire's rate of advance. And with the wind, there's another related size-up consideration: topography. Canyons or ravines like West Creek's exacerbate the situation. Canyons often channel wind, stepping up the wind speed and increasing the fire's intensity. In our scenario, the fire is backing down the hill. But what would happen if the fire was moving up the slope? As you can see, the angle of the terrain tilts the flame into the fuel, just as the wind did. The spread rate increases. The steeper the grade, the faster it spreads. If West Creek had been located above the canyon, say near this ridge, we'd be looking at a fire with higher spread rates and higher intensities. We would have little time, if any, to prepare the homes in the neighborhood. Fortunately, with the homes situated downhill from the fire, we won't have to respond to the combined impact of wind and slope. We might have some valuable time to mitigate around the homes. So what have we learned from our size-up? Our most important conclusion is that this fire has intensified to extreme conditions. Due to the area's fuels, temperature, humidity, and wind, the surface fire has reached a high rate of spread. Moreover, the wind is sweeping firebrands ahead of the fire, causing prolific spotting at the base of the canyon. The bad news is that we can't contain the fire, or even slow its encroachment on the residential area. Our only good news is that the fire is moving down the slope, and enough distance exists between the fire and the community to give us some time before it arrives. It's clear that a containment approach is not feasible here, so we'll start triaging homes as part of a mitigation strategy. It's important to understand that our knowledge of fire behavior is based on scientific research. Years of experiments and analysis have given us guidelines to what a fire will and won't do. Science provides us with a set of physical principles that we apply to each situation. But situations are different, and fire is dynamic. Winds can gust and shift direction suddenly. Flames can flare up, increase spread rate, and change direction without warning. So your response must be equally dynamic. You must continually reassess your situation. Think about what can happen next, anticipate the possible worst case, and then change your tactics accordingly. And if you find yourself in an unfamiliar area, consult with local experts who know about the area's fuels and weather patterns. We've determined that the fire will probably arrive here soon. So how should we anticipate its behavior here in West Creek?
The firestorm rages on across the inland northwest tonight. The wind and dry conditions stack the chips in the fire's favor.
The first thing to understand is that fire doesn't behave as the media usually portrays it. No matter how large the flames may appear, fire does not descend and consume a community like a giant tsunami. Rather, fire progresses as a series of ignitions, and it follows the same rules regarding topography, weather, and fuels that we just applied in the wilds. Identifying the fuels in the fire's path gives you a clue as to how the fire will likely advance. Fuels come in all forms in the interface, from natural fuels such as grass, pine needles, shrubbery, and trees, to fuels introduced by humans, lawn furniture, fences, vehicles, even the structure itself. So how do you determine which of these fuels will ignite and which won't? To answer this question, let's begin with some scientific basics. When we talk about fire, we're talking about combustion. And combustion occurs by transferring energy into a fuel, by thermal radiation, convection, and conduction. Energy is conveyed to the surface of a fuel, usually by thermal radiation or convection. Thermal radiation occurs when heat is transferred without the fire touching the fuel. Energy is instead radiated through space to the surface of the material. Convection occurs when energy, usually in the form of a flame, directly touches the surface. Now, if only the surface were to ignite, a fuel would burn out very quickly. So in order to keep a tree trunk, a wall, or any other woody material burning, energy must somehow be conveyed to the object's interior. That's where conduction comes in. Once the surface of a fuel heats up, the energy is then transferred directly from the exterior of the object into its interior. This process causes more of the object's mass to combust and enables the fuel to burn longer. So how does this figure into our size up? Because it helps explain what will and won't happen during a fire. For example, let's look at how distance factors into structure ignition. You might be surprised to learn that large flames often do not ignite homes. The reality is that under most conditions, an intense fire burning farther than 100 feet away from a structure does not transfer enough radiant heat to ignite the structure. More often than not, small ignitions and spotting cause the destruction of homes. That's because these small flames either come in direct contact with the structure or are close enough to radiate sufficient heat to ignite it. Another surprising scientific fact involves fire and time. Intense fires usually burn out very quickly, so quickly in fact that they don't burn long enough to ignite buildings. That may sound counterintuitive. Because humans are sensitive to heat, we assume that other materials are as sensitive as we are. But a fire that will radiate enough heat to give us a second-degree burn in 5 seconds takes over 27 minutes to ignite wood. Experiments have shown that heavy fuels such as a wall, door, or roof must be exposed to radiant heat for a long period of time before they'll ignite. So what is the rule of thumb here? Generally, fuels with a lot of surface area and little mass, such as grass and dry pine needles, will ignite and burn quickly. And heavy fuels like tree trunks and 2x4s, with a large mass for its surface area, ignite and burn slowly. So let's now apply this science to West Creek and anticipate what happens when the fire arrives. First, we can assume that the fire's advance will slow down a little. That's because it is moving from the dense woods into a residential area where the fuel continuity is broken by roads and yards. By looking at the available fuel, we can determine which homes are vulnerable and which aren't. For example, in this particular case, this house is vulnerable because of a continuous pine needle fuel bed leading up this slope all the way to this location under the shrubs. We can see the pine needles and the leaf material and the dead grass potentially igniting the shrub canopy, which then leads right directly to the house. If this shrub canopy becomes involved in fire, it's going to increase the intensity, most certainly allowing flames to touch this structure. In this case, it's not the tree canopy that's the problem, and it's not a problem because we can't see the house. The problem is the continuous pine needle fuel bed leading directly to the house. This house is much less vulnerable to fire. We still have a slope, we still have tree canopy, we still have a surface fuel bed, and we've got shrubs, although some of the shrub vegetation has been removed. A fire burning in this surface fuel bed will stop before it gets close enough to burn the house. So far, we've talked about what will happen to West Creek when the fire arrives. Now let's look at another threat that will occur long before the surface fire gets close. We're talking about firebrands. Let's head back up the hill to where the fire is. As you'll remember, our fire is burning in the canyon woods about 1/4 mile above the community. The fire has become so intense that it's lofting firebrands, or embers, into the air. As you'll also recall, a 30-mile-per-hour wind is blowing down the canyon, and this wind is carrying these firebrands and dropping them on or near the homes. So how do you anticipate their impact on West Creek? You can assume that the firebrand shower will cause multiple ignitions in the surface fuels. Now that doesn't mean that every ignition will be harmful or has to be extinguished. On the contrary, by applying your knowledge of fire behavior, you can predict if the spot fires will directly ignite a structure or create a series of ignitions that ultimately leads to it. You can also assume that some firebrands will land directly on or adjacent to the structures. You can determine where they'll likely land by looking for places where leaves or ash from the fire have already collected. For example, this house is vulnerable because firebrands could land here, in this pile of leaves right next to the structure. Firebrands also pose a very serious problem on flammable roofs. This home's wooden shingles make it highly vulnerable. The embers might wedge between them and burn unattended long enough to ignite the roof. On the other hand, this home, with a tile roof and stucco siding, should survive the onslaught of firebrands. They'll probably burn out harmlessly on these fire-resistant materials. However, look over here. This is a perfect spot for a firebrand, a patio cushion. Remember, as we size things up, a cushion is not a cushion. Rather, it is a fuel that can easily combust. A fuel that could ignite this chair, the deck, the house. Fortunately, cushions can be easily mitigated. The key to anticipating a fire's behavior is to stop thinking of these structures as homes and to start thinking of them as fuel. For example, once this house is engulfed in flames, it behaves exactly like any other fuel. It can ignite other objects, including nearby structures. How dangerous is a burning home? Well, consider that a burning structure can potentially ignite another structure within 50 feet of it. In other words, if this home goes up, it could ignite its neighbor over there. And if West Creek were a higher density community, like this, we might be looking at a series of structure-to-structure ignitions that could quickly outstrip even the largest firefighting resources. So far, we've covered many of the variables that you'll encounter in the interface. Now it's time to wrap up and assess what occurred in our hypothetical scenario. We knew from our initial size-up that this fire couldn't be contained before it entered West Creek. First, firebrands dropped into the community, causing spotting and small structure ignitions. Now let's fast forward a little. After a while, the intense surface fire in the forested area moved into the neighborhood, just as we anticipated. As you can see, a few highly vulnerable homes in West Creek did catch fire. Once they became engulfed, the firefighters moved on to protect other homes, effectively saving many at the loss of a few they couldn't protect. Fast forward again. Most structures survived the flames. Many were scorched but didn't sustain ignitions. Once the surface fire passed, the firefighters returned and put out any remaining small ignitions before they could significantly involve the homes. The fire eventually stopped beyond the community. Altogether, only 3 homes were destroyed. This didn't happen by chance. Most houses had little risk of being ignited in the first place, which enabled the fire crews to implement an effective wildland urban fire strategy. The firefighters correctly anticipated the fire's behavior. They realized that they couldn't contain it, so they responded with a strategy that protected the structures that could be protected. In short, they didn't stop the wildfire. They avoided a disaster in West Creek Village. In this fictional scenario, we sketched out some basic principles of wildland urban fire behavior. But clearly we've only presented one example. Each fire will present its own set of conditions and unfold in its own unique way. And these conditions will change while you're working the fire. Weather, topography, and fuels all contribute to erratic fire behavior. Fire is dynamic, so learn as much as you can about wildland urban fire behavior. When the dispatch comes in, your knowledge and training will help determine whether or not you respond effectively to a fire involving your community.